Welcome to this video on fluid mechanics in food processing. Fluids are substances that flow under shear stress, and this includes both liquids and gases. Think about the air inside a water bottle. It flows, so it's a fluid, just like the liquid it contains. Fluids behave differently based on their properties. When looking at water, milk, honey, and oil, we encounter concepts like density, which describes how heavy a fluid is for its volume, and specific gravity, which compares a fluid's density to that of water. Watch how water, cooking oil, and honey pour differently into these beakers. The varying speeds at which they flow highlight the concept of viscosity, or the internal resistance a fluid has against moving. By definition, a fluid deforms continuously under shear stress. Whether it's a gas or a liquid, the way they flow determines how we process them in the food industry. Understanding these differences helps us predict how they interact on surfaces like ramps. Viscosity represents internal friction. Water flows easily with low viscosity, while honey resists flow due to high viscosity. This property is governed by Newton's Law of Viscosity, relating shear stress to velocity gradients. This spectrum shows how viscosity varies significantly from air to honey. In food engineering, we use these values to design machinery, such as pumps for chocolate or filling lines for milk, ensuring efficient production flows. Have you ever wondered what happens when a balloon is left in the sun? The air inside heats up, causing the gas to expand. This demonstrates the critical relationship between pressure, volume, and temperature. The equation of state links pressure, volume, and temperature. In food processing, these variables are interdependent. Changing one, like increasing pressure in an evaporator, directly impacts the others, affecting the fluid state. For many engineering calculations, we use the perfect gas model. While real gases are complex, this idealization allows us to accurately model processes like nitrogen flushing in snack packaging, ensuring shelf stability. The ideal gas law is defined by the formula PV equals nRT. It is a powerful, simplified tool that engineers rely on to manage pneumatic conveying systems and other gas-based operations within a factory. The standard form, PV equals nRT, uses the number of moles. Alternatively, we can use the mass-based form, PV equals mRT, using a specific gas constant. Both forms are essential for calculating fluid behavior under different conditions. Vapor pressure measures a liquid's tendency to escape into a gas. By controlling this, food engineers use vacuum evaporation to boil fruit juices at lower temperatures, effectively preserving essential vitamins and flavor profiles. Cavitation is a dangerous phenomenon where local pressure drops below vapor pressure, causing vapor bubbles to form and implode. This can destroy pump components, causing severe noise and loss of efficiency in your systems. Compressibility describes how volume changes under pressure. Gases are highly compressible because of the empty space between molecules, whereas liquids are virtually incompressible. This is why we use liquids in hydraulic systems. Finally, elasticity is the fluid's ability to return to its original volume after pressure is removed. Understanding this is vital for designing safety relief valves, helping to mitigate dangerous shock waves in pressurized pipelines. Let's apply these principles to a case study, selecting a pump for a chocolate factory. Engineers must account for the high viscosity of chocolate, the temperature-dependent equation of state to prevent blockages, and the risk of cavitation if suction pressure is too high. To summarize, always remember these 5 points. Viscosity dictates pump sizing, the equation of state links fundamental variables, gases often behave as ideal, cavitation is a major risk when pressure drops, and fluids vary significantly in compressibility and elasticity. Consider this challenge: transporting cooking oil through outdoor piping in winter. How do viscosity and the equation of state interact here? Discuss this with a classmate to determine the best engineering solutions to keep the oil flowing. For your assignment, explain why honey is harder to pump than water, perform your viscosity calculations, and try the syringe test at home to feel the difference between gas and liquid compressibility. See you in the next lecture on fluid statics.